Hello everyone, welcome back to TechOps tutorial. In this video, we are going to talk about very important topic in Kubernetes, resource request and limits. If you are running application in Kubernetes, you should know how much CPU and memory your pod needs. And Kubernetes actually use these values to decide where your pod will run and how much it can use. So in this session, I will first explain the basic idea in simple words and then we will jump into a hands-on demo. By the end of this video, you will understand how Kubernetes schedules pod based on the resource you define. We are also going to look at a few important concepts like qos classes and scheduling behavior. So let's get started. Before we jump into actual requests and limits, let's quickly understand why resource management is important in Kubernetes. First, it prevents overuse. If a pod starts using too much CPU or memory, it can affect other applications which are running on the same node. So setting limits protects the cluster and avoids unexpected crashes. Second, it helps with fair distribution. Kubernetes wants to allocate a resource in a balanced way. When you define a request, the scheduler knows exactly how much your pod needs and place it on the right node. And finally, it improves cluster stability. When resources are controlled properly, you avoid situations where one application takes too much and affects other. This keeps your cluster healthy and reliable, especially during heavy workloads. So overall, resource management keeps the cluster protected, efficient and stable. Now let's talk about a resource request. This is basically the minimum amount of CPU and memory your pod needs to run properly. For example, here you can see a CPU request of 250 milli-CPU, which is 0.25 of core, and a memory request of 256 MI. MI means megabytes. When you set these values, Kubernetes uses them during scheduling. So the scheduler will only place this pod on a node that has at least this much free CPU and memory available. On the right side, you can see a simple YAML. Inside the container section, we define our request. This tells Kubernetes, my pod needs at least this much to run. Please schedule me on a node that can support it. So in short, requests are the guaranteed minimum resource your pod needs, and the Kubernetes use these values to decide where the pod should run. Alright, now let's talk about resource limits. If you remember, requests were the minimum your pod needs. Limits are the opposites. They are the maximum amount of CPU and memory your pod is allowed to use. On the left, you can see two bars, one for CPU and one for memory. Each bar shows the current usage and then the limit. So in this example, the pod is using around 400 M CPU and the limit is 500 M. Same with memory. It's using about 410 MI and limit is 512 MI. This means the pod is getting close to the top, but it still hasn't crossed the limit yet. Now, what happens if the pod goes over? For CPU, Kubernetes will slow the container down. It won't kill it, it just throttle it so it cannot use more than the limit. But for memory, it's different. If the pod crosses the memory limit, the Linux kernel will terminate the container with out of memory error. This is hard limit and it's why setting memory limit is very important. On the right side, you can see a simple YAML file. Inside the containers section, we have both a request and limits. Here we set a CPU limit of 500 M and a memory limit of 512 MI. That is a maximum memory. This tells the Kubernetes, my pod should never use more than this amount. If it does, enforce the limit. So in short, limits protects your cluster by making sure pods don't use more resource than you are allowed. CPU gets throttled, memory can cause an out-of-memory kill, and together these limits keeps the node stable. Now let's look at request and limits side by side so you can clearly see the difference. On the left we have a request. Requests are the minimum amount of CPU and memory pods needs to run. This is what the scheduler uses when deciding where to place your pod. So if your pod requests a certain amount of resources, Kubernetes will only place it on a node that has at least that much free capacity. In short, requests affect scheduling and node selection. On the right, we have the limits. Limits are the maximum amount of resources a pod is allowed to use. These are enforced by the kubelet on the node. If your pod tries to use more CPU than its limits, it gets throttled. If it goes over its memory limit, it might get killed. So limits affects how the container behaves at runtime. So to keep it simple, request decides where the pod will run. Limits control how much the pod can use once it's running. Together they help you manage the resources in a clean and predictable way. Before we go deeper, let's quickly clear up how CPU and memory units works in Kubernetes. These numbers can look confusing at first, but they are actually pretty simple once you see them side by side. Let's start with CPU. Kubernetes measures CPU in millicores, so 1000 M equals to one full CPU core. That means 500 M is half a core, 250 M is a quarter of core, and so on. The gauge on the left shows this idea from 100 M up to 500 M and beyond. Now let's move to the memory. Memory is measured in MI and GI, and just like in normal computing, 1024 MI is equals to 1 GI. So when you see the values like 256 MI or 1024 MI, they are just a different values of memory your pod might need. You will see these units all the time in your YAML files. For example, if you set CPU 250M, that simply means the container gets 0.25 of your CPU core. And if you set memory to 1024 MI, that means 1 GI of RAM. So don't worry, once you understand these basic units, reading Kubernetes resources values becomes much easier. Alright, now let's look at what happens when you don't set a resource request and limits. This is where things get messy. On this slide, you can see the idea of cluster chaos. And honestly, that's exactly what happens in the real life. When a pod don't have the limit, they can grab as much of CPU or a memory as they want. So one pod might suddenly start consuming a way more resources than actually needs. And when that happens, the node can get overloaded. Now once a node is overloaded, everything running on this node starts to suffer. Other pods may not get the CPU or memory they need, and this leads to resource shortage. So even healthy workloads can slow down or crash just because one pod is using more than it should. And it does not stop here. If the pressure keeps building, the node itself can become unstable. You might see pods getting evicted, random restarts, or even the whole node going down. That's why a Kubernetes gives us that warning sign on the slide. It's a reminder that without a request and limits, you are basically running your cluster with no rules. So the takeaway is simple. Always define both resource request and limits. It keeps your node stable, your workload healthy, and your cluster predictable. Now let's walk through how Kubernetes decide where to run a pod. At the top, you can see few pods waiting in the queue. These all are pending pods. They are ready to run, but they haven't been placed on any node yet. The scheduler steps in and checks how much CPU and memory each pod needs. Then it looks at the node in the cluster to see which one has the enough free space. In this example, we have the 3 nodes. Node 1 is already pretty full. Node 3 is almost completely full. Both CPU and memory are very high, but Node 2 still have a plenty of room. So the scheduler picks Node 2 because it can actually handle the pod's requirement. That's why we see the selected on Node 2. This is basically how Kubernetes makes sure pods runs on the right node. And one important thing, if none of the nodes have enough CPU or a memory, the pod will stay in pending state. It won't start until there is enough free resources somewhere in the cluster. So in short, the scheduler checks what the pod needs, checks what the nodes have, and then place the pod on the best fit. Now let's talk about QoS classes in Kubernetes. QoS simply means quality of service, and it tells Kubernetes how important a pod is when the node is under pressure. You can see three levels here. At the top, we have a guaranteed. This is the highest priority. A pod is guaranteed when its CPU and memory requests and limits are exactly the same. These pods are the safest. They are the last one to be evicted if the node is running out of the resources. In the middle, we have Burstable. This is the most common group. These pods have a request and limits, but the values are not equal. They get medium priority, so the Kubernetes will evict them only after best effort pods. At the bottom, we have best efforts. These pods have a no request and no limits because they don't reserve anything. They get the lowest priority and they are the first to be evicted when the node is under pressure. The arrow on the right shows the eviction order. Best effort first, then the burstable, and the guaranteed is the last. So in simple term, set your request and limits properly if you want Kubernetes to treat your pods as important. Alright, before we move on, let's do a quick recap using a real world example. Think of your Kubernetes cluster like a busy restaurant. On the left, you see the people with a request. This is like having a table reservation. They have booked a spot, so the restaurant guarantees them a table. In Kubernetes term, this means the pod has guaranteed resource. Next, we have a burstable. This is more like flexible booking. You still get a table and you have a guaranteed resource, but you also have some extra room to grow if the restaurant is too busy. Now, on the right, we have no request and no limits, basically walk-ins. They might get a seat, but they can be asked to leave if the restaurant gets full. These are your best effort spots. And finally, limits works like a time cap. You cannot stay longer than your allocated time. In Kubernetes, limits stop your pod from using more CPU or memory than what you set. So overall, running a resources in a cluster is a lot like managing a busy restaurant. You want fairness, you want balance, and you want to make sure everyone gets what they need without overloading the system. Alright, let's begin with a quick scheduling demo. The goal is simple. We will see how Kubernetes reacts when the pod has normal resource request versus when the request exceed the node capacity. First, we will deploy a pod with reasonable CPU and memory values. It should schedule immediately. Then we will increase the CPU request beyond what node can offer. A pod will go pending. Finally, we will lower the request back to our valid values and see Kubernetes schedule it again. This demo will show you in real time how resource requests directly influence pod scheduling. Let me access the terminal. On my screen, you can see the minikube status. It is running and kubectl get nodes output as well. We will see how request affects scheduling, how limits control resource usage, how CPU is throttled, and memory can trigger out of memory and get kills, and how QoS classes determines pod priority. I have already created a YAML file. Let me show you before deploying. This is the YAML file. This pod requests 500 M CPU and 256 MI memory, a value that most nodes can handle easily. It should get scheduled without any issue. Let me deploy it. kubectl apply-f resource-demo.yaml. Pod is get created. kubectl get pods. As expected, a pod is running. Kubernetes found a node with enough free resources and scheduled it immediately. Now let's see how many CPU and memory minikube node is using. kubectl describe node minikube. Here's the capacity. CPU is 4 and memory is near about 11.7 GB. You can run grep-a5 capacity. You'll get the output. This shows my minikube node has 4 virtual CPUs. So any pod requesting up to 4 CPUs will still get scheduled. To force pod in pending state, we need to set CPU request to 4500 M CPU, or the other option is to start the minikube with custom CPU capacity like 1 CPU while starting itself. Let's see the demo. Just for information, if you want to reduce the CPU to force pending state, you can delete the minikube and start it again with this command minikube. As of now, I'm not doing this, just I want to show the command. CPU equals to 1 and memory I will give 2048 and driver I'm using Docker. This is the command. And if you want to set 2 CPU, you can give here 2. And if you want 3 CPU, you just rename with the 3. And if you want a 4 CPU, you can change this with 4. The command will be like not CPU, it's CPU's yes. You need to give S equals to 4, followed by -- memory equals to 2048. If you want to change the memory to 4 GB, you need to give 4096 and then 4096 and then - driver equals to Docker. This is just a info. I'm not doing this. Instead, what I will give, as we have a 4 CPU, I will allocate a pod with 4.5 CPU so that it will go into a pending state. We can check the minikube node CPU capacity using kubectl describe node. And if you want to change the CPU for testing scheduling behavior, you can restart the minikube server with the -CPUs flag as I shown the command above. These are the command. For now, what I will do, just delete the pod and update the YAML with 4.5 CPU so that the pod will force to a pending state. kubectl delete pod, give the pod name. After deleting, I will edit the same YAML file, change the value 4500 and here also 400 M. Now the pod requests 4.5 CPUs. My minikube node does not have that much free CPU, so Kubernetes cannot schedule it. The pod will go into pending state. Let's see now. kubectl apply -f resource-demo.yaml. The pod is created. Kubectl get pods, check the status. The status is in pending state. Kubernetes checks every node but could not find enough free CPU. The pod remains pending until the resource becomes available. Let's see. Kubectl describe pod, give the pod name resource-demo. In event message, check 0/1 nodes are available, 1 insufficient CPU. This confirms the pod is pending because no nodes can satisfy the CPU request. So we can lower the CPU request to schedule the pod. Kubectl delete pod resource-demo, give the pod name. Once it get deleted, revert the YAML. I have reverted the value from 4500 M to 500. We can change this to 1 CPU. Save it. I reverted the YAML file. If you want, I will get it. Apply it. This will take time to get created. Here you can see the pod is running. As soon as we lower the request to something the node can handle, Kubernetes schedules the pod immediately. Request decides scheduling and limits control the maximum usage. For optional verification, we can use kubectl top pod, give the resource name, give the pod name. So the matrix, we need to install the matrix server here. Kubectl get pods -n. In kube-system, the matrix server will be there. Let me run this. Grep matrix. Matrix server is running. Now we can see the output. Here you can see the board name and the CPU core is 0M, memory is 4MI. CPU core is shown in milli-CPU, means M. Here 0 means the pod is using almost no CPU. If it shows 120M, then it will be equal to 0.12 CPU. Here memory is shown in megabytes, that is MI. 4MI means is equals to 4 into 1024 into 1024 bytes. Kubernetes guarantees at least the requested resource and enforce the limit if usage grows. Here we see the pod is running, CPU usage is very low, 0 milli CPU, and the memory usage is 4 megabytes. The kubectl top command won't work by default because Kubernetes does not collect the resource usage on its own. It needs the matrix server. Once it's enabled, we can see the real-time resource usage for pods and nodes. I have already installed matrix server. That's why we are able to see the resource usage for this resource-demo pod. CPU is measured in milli-CPU and the memory is megabytes. This output shows how much CPU and memory the pod is actually using. To check if the matrix server is running, you can use kubectl get pods -n kube-system followed by grep matrix. This is the command. MI means megabytes and M means milli-CPU. And if you want to install the matrix server, you can use the command minikube addons enable matrix hyphen server. This will again get installed and enabled. I have already installed this, so let's move to the next step. Once this is done, let's clean up the resource. kubectl delete pod resource hyphen demo, and that's a wrap up CPU and memory request scheduling. Now we will see the CPU throttling limits in action. Deploy a pod with CPU limits. I have already created a YAML file. I will show you. This is the YAML file. This pod requests 200 M CPU with a hard limit of 300 M. Kubernetes guarantees at least 200 M CPU but will never let it exceed 300 M CPU. Let's deploy kubectl apply-f CPU -demo YAML kubectl get pods. It's running. The pod is running. Let's generate CPU load to see the throttling. I will log into the pod kubectl exec-it, give the pod name CPU-demo-sh. Once we are in the shell, I will run while true this infinite loop tries to consume 100% CPU continuously. Kubernetes will throttle it near to 300 M limits. Open a new terminal and run kubectl top pod CPU-demo. For continuously monitoring CPU usage, you can run with watch. This is a Linux command. kubectl top pod CPU-demo. So continuously it will start monitoring. CPU usage increase gradually because Kubernetes reports it periodically through the matrix server. Here the pod requests 200 M CPU and has a 300 M limit. Even though our loop tries to use 100% CPU, Kubernetes throttle it near 300 M. We can watch it live using watch kubectl top pod followed by the pod name to see the usage climb until it hits the limit. Sometimes a minikube, you may see the value slightly below the limit like 250 M plus. This happens because the matrix server reports CPU in intervals. The node has the limited CPU and the system process also consumes some CPU. This number gives an approximate view of CPU throttling, not the exact CPU being used at every second. The container is throttled near 300 M CPU, never exceeding the limit. Let's go to the previous terminal and press Ctrl C in the pod shell and exit. kubectl top pod CPU demo. CPU usage drops immediately after stopping the load. Here you can see now it's 113 M. Let's clean up now. It's again getting dropped as we close the while loop. kubectl delete pod CPU-demo. And that's the CPU throttling in action. Now we will see the memory limits and out of memory kills, which we call as OOM kills. This will take some time to delete. Let this get deleted. I have already created a YAML file for this demo. I will show you with the memory-demo YAML. This is the YAML file. This pod is asking for just 10 MI of memory and it allows us only up to 20 MI. But inside the container, we are tracing it to use around 150 MI. So the moment memory usage crosses the 20 MI, Kubernetes will kill this container. So let's apply it. kubectl apply -f memory-demo get pods. Now let's watch what happens when it tries to use more memory than the limit. Here we have used the trace command to 150 memory. So we can see with kubectl get pod memory-demo-w. So 2 times it got restarted. And now the second time it got restarted. Here I am watching the pod in real time and you can see it quickly goes into out of memory kill. This means the container tries to use more memory than the limit was set. So the Kubernetes stopped it. It tries to start again but it keeps failing. After a few restart attempts, the pod moves into a crash loop back off, which simply means it's stuck in a restart loop because every time it starts, it again hits the memory limits and get killed. We can see in another terminal, we can run this command kubectl describe pod, give the pod name memory demo. Here you can see the status. Here you can see the state. It's terminated, reason is out of memory killed. Last status is terminated. Here also you can see in events, back of restarting failed container demo in the pod. Restart count keeps on increasing to 5. This describe output confirms it. The pod was killed because it exceeded the memory limit. Unlike CPU, memory cannot be throttled. If your container uses more than what you allowed, Kubernetes immediately kills it. kubectl delete pod memory. I'm cleaning up the resource. Memory-demo and it got deleted. And that completes our memory limit demo. This clearly shows why using the right memory request and limit is important. Now let's see qos-classes demo. Step 1. I have already created the YAML file. Let me cat it qos-. This is the YAML file I have created. Here the CPU and memory requests are equal to limits. You can see both are same. This gives the pod guaranteed QoS, which means it has the highest priority of eviction in case of node resource pressure. Next YAML is qos-. This is the next YAML file for Burstable pod. Here, when requests are less than the limits, you can see the request is less than the limits. The pod gets Burstable QoS. It can use extra resources when available, but its eviction priority is lower than the guaranteed pod. And the another YAML file I have created is qos-bestefforts. This is the small YAML file example. If the pod has no request or limits, in earlier YAML you can see I have defined request and limits, but here in besteffort YAML we have not defined any request or limits. It gets a best effort QoS, meaning it has the lowest eviction priority. Let's apply all the YAML files. kubectl apply -f qos-guaranteed.yaml. It's not q, GUAR. Next, apply kubectl apply -f qos-burstable YAML file. kubectl apply -f qos-bestefforts. kubectl get pods. All three pods are running. Each has the different QoS classes based on its resource configuration. So to check QoS, we have the command kubectl get pod QoS. We need to give all pods. First is guaranteed, then burstable, then bestefforts -o equals to custom column name. I will share this command in description. metadata.name qos status.qos. Guaranteed pod have the highest priority, burstable pods have the medium priority, and the best effort pods have the lowest. Kubernetes use this information to decide which pod to evac first when the node runs out of the resource. Let's clean up. kubectl delete pods. Give all the pod name. That concludes the QoS demo. Today we have explored the Kubernetes resource management, request decides scheduling, limits enforce CPU throttling, memory violation triggers out of memory kills, qos classes determines eviction priority. Understanding these fundamentals ensures your workloads runs efficiently and your clusters stay stable. Let's move to the slide. Alright, let's wrap up with a quick recap and some best practice. First, always define both request and limits for every container. This ensures predictable behavior and avoid scheduling surprises. Second, right size your resources. Don't over request CPU or memory. Monitor actual usage and adjust based on the real data. Third, use the cluster level control like resource quotas and limit ranges to enforce default and maintain balance across namespaces. Finally, understand the QoS classes. They influence the scheduling and eviction, so choose the right class for each workload. By following these basics, your clusters stay healthy, workload runs smoothly, and avoid unnecessary troubleshooting. That's a wrap up on resource request, limits, and QoS classes and how Kubernetes schedules pod based on them. If you found this video helpful, don't forget to like, share, and subscribe to TechOps tutorial for more Kubernetes and DevOps tutorial.